Hello, everyone! In this lecture series, we are going to learn one of the most important methods used for analyzing statically indeterminate structures, the method of consistent deformation, also called the force method. Now, the question is, why do we need this method? Because for a statically determinate structure, equilibrium equations are sufficient. But when a structure becomes statically indeterminate, equilibrium equations alone are not enough. So we need one additional concept. And that concept is called compatibility of deformation. Let me write that. Compatibility plus equilibrium equals solution. Here, compatibility means that the structure must deform in a physically possible manner. The supports, joints, and members must remain connected after deformation. The force method uses this compatibility condition to obtain the extra equations required for analysis. The general workflow is very simple. First, identify the indeterminacy. Second, remove the extra reaction. Third, calculate the deformation. Fourth, enforce compatibility. And finally, determine the unknown reaction. In the next poster, let's examine a beam and determine whether it is statically indeterminate. Let us start with this beam. It is fixed at A and supported by a roller at B. A concentrated load P acts on the beam. Before solving anything, we must determine the degree of indeterminacy. Let's count the unknown reactions. At A, we have AX, AY, and MA. That gives us 3 unknowns. At B, we have one reaction, BY. So total unknown reactions are 4. Unknowns equals 4. Now, how many equilibrium equations are available? For a planar structure, sigma fx equals 0, sigma fy equals 0, and sigma m equals 0. That means only 3 equations. DOI equals unknowns minus equations, equals 4 minus 3 equals 1. So the beam is statically indeterminate to the first degree. That means we need one additional equation. And that additional equation will come from compatibility. Let's see how. The first step in the force method is choosing a redundant. Let us choose reaction BY as the redundant. If I remove this reaction, the structure becomes a cantilever beam. This new structure is called the primary structure. Notice that the primary structure is now statically determinate. Now apply the external load P. What happens? The beam deflects downward. Most importantly, point B moves downward. Let this displacement be delta B. Since support B was removed, the beam is free to move there. This displacement is very important because later we will force it to become 0 using compatibility. The force method is based on superposition principle. The idea is simple. The actual beam can be represented as primary structure plus effect of redundant reaction. In the primary structure, load P causes a downward displacement, delta B. Now let us apply the redundant reaction BY separately. This force causes an upward displacement. Let us call it delta BB dash. Now, think about the actual structure. Support B cannot move, so the downward displacement and upward displacement must cancel each other. Delta B plus delta BB dash equals 0. This is our compatibility condition. Now we need to calculate the upward displacement caused by BY. Instead of directly applying BY, we first apply a unit load. When a unit load acts at B, the resulting displacement is called FBB. FBB equals displacement at B due to unit load at B. This quantity is called the flexibility coefficient. If one unit load produces displacement FBB, then BY load will produce BY times FBB because the structure behaves linearly. Delta BB dash equals BY times FBB. Now we can substitute this into the compatibility equation. Till now, we selected a force as redundant. but we can also choose a moment. Suppose we choose the fixed end moment MA as the redundant. Removing MA converts the support into a pin. Load P causes a rotation theta A. Now apply a unit moment at A. The resulting rotation is called alpha AA. Alpha AA equals rotation due to unit moment. This is called the angular flexibility coefficient. Just like force times flexibility equals displacement, similarly, moment times angular flexibility equals rotation. Theta AA dash equals MA times alpha AA. And since the actual support is fixed, total rotation at A must be 0. Now let us move to a more complicated structure. This beam has 4 supports. When we count the reactions, we find that the structure is indeterminate to the 2nd degree. Therefore, we need 2 redundants. Let us select BY and CY. After removing these supports, the beam becomes the primary structure. Under the external loads, point B moves downward by delta B and point C moves downward by delta C. Since 2 redundants exist, we will need 2 compatibility equations. Now we need multiple flexibility coefficients. Let us first apply a unit load at B. This produces displacements at both B and C. FBB, FCB. Next, apply a unit load at C. This produces FBC and FCC. These coefficients form the flexibility matrix. This matrix helps us write 2 compatibility equations and solve both unknown reactions simultaneously. Let us summarize the complete force method. Step 1, determine degree of indeterminacy. Step 2, choose redundants. Step 3, create primary structure. Step 4, apply superposition. Step 5, determine displacements. Step 6, calculate flexibility coefficients. Step 7, write compatibility equations. Step 8, solve for redundants. Step 9, apply equilibrium equations. Step 10, draw SFD, BMD, and deflected shape. The beauty of the force method is that it converts a statically indeterminate structure into a statically determinate structure, and then restores the removed reactions using compatibility conditions. Once you understand compatibility, flexibility coefficients, and superposition, the entire force method becomes very straightforward. In the next lecture, we will solve numerical examples using the method of consistent deformation step by step. Thank you for watching.